All right, today we're going to talk about a concept called differentiability. Differentiability. That is a 7-syllable word. Counted the syllables last period. Differentiability. Okay. Now, anybody got a guess as to what this means?
It's the ability to find a derivative. The ability to find the difference between the derivatives.
Okay. Did you know that, or did you look at his notes? Okay. All right. His ability to do something, and most people were thinking different as in difference as in subtraction, but that's not what it's meaning here. A differential is another name for a derivative. So a differentiability is the ability to be differentiated, which is the ability to have its derivative taken. Okay? So the definition of differentiability is the ability to take the derivative. The ability to take the derivative. Does every function have a limit? Does every function have a limit? No. Some functions do and some functions don't. Is every function continuous? No. Some are and some aren't. And the same thing is true with differentiability. Do all functions have a derivative at a point? And the answer is no. Some do and some don't. And today we're going to learn how to tell the difference between the ones that do and the ones that don't, both graphically and algebraically. Okay? So let's kind of build up to what exactly has to be true in order for a function to have a derivative. And it's a stair-step process. First, we talked about limits. A limit exists at x equals a if what?
The LHL and the RHL.
The left-hand limit and the right-hand limit are equal, exactly. Left-hand limit is equal to the right-hand limit. Straighten that out a little bit. There we go. So, the simplest way to look at it, if the left and right-hand limit are the same, it's going to have a limit. If they're not, it's not. Okay, second was, what was the second thing we studied after limits? Continuity, very good. Continuity. A function is continuous at x equals a if what? LHL equals RHL equals, what's the third?
F of A.
F of A in this case. LHL equals RHL equals F of A. Okay. Now let's make sure we understand this. True or false? Every function that is continuous has a limit at that point. That is true. Every function that has a limit is continuous at that point.
False.
That is false. What is it? What is a counterexample to prove that it's false? What would it look like? It has a limit, but it's not continuous.
Point. It's like a line where there's a whole jump.
Right. A hole in the graph. Point is continuity. Counterexample for that. It has a limit, but it's not continuous. Does that make sense? Okay? So that's the relationship between those two. The third one, and the one for today, is differentiability. The word is so long. And by the way, most of the time through the notes, I'm going to abbreviate differentiability as DIFF, and that is allowed on the AP exam. It is allowed. Okay?
So if you abbreviate it like wrong, like they will take off.
No. But if they don't understand what you mean, they won't give you credit. That's what the point is. Okay, so what does this, in order to be differentiable, what has to happen? That's what I'm about to tell you. F of x is differentiable, which I'm going to then write DIFF, because that's allowed, at x equals a if ... Two things have to be true. Item number 1, f of x is continuous at a. F of x is continuous at a. If it's not continuous, it can't have a derivative. Now think about it. You were just telling me that a function that has a limit but is not continuous is like a hole, right? Can you have a derivative at a hole? Can you have a slope at a hole? No. So it has to be continuous in order to be differentiable. Just like it has to have a limit in order to be continuous. Are you hearing what I'm saying? Okay. That's the first thing that has to be true. The second thing is that the limit as x approaches a from the left of the derivative has to equal the limit as x approaches a from the right of the derivative. So the left and right hand limit of the derivative have to be equal in order to be differentiable. Now what does that exactly mean? As you're on a curve, you know that slopes are slowly changing, right? So, as you're coming up a curve this direction, the slope here might be 1, might be a half, a quarter, an eighth, and so on. But as you get to the top of the curve, for example, the slope is getting closer to 0. And on this side, the slopes are negative, but they're also getting closer to 0. So, the slopes are approaching each other. That's what I'm saying. I'll show you a counterexample where that doesn't happen in just a minute. But the slopes, that's the key. The slopes have to be approaching the same number. Not the function, the slopes. Bless you. Okay. Let's take a look at an example of one that is continuous but not differentiable. And that is f of x equals the absolute value of x. That is the most common continuous non-differentiable function. And we're going to go at it as if we don't know that, and I'm going to prove it to you. Is it differentiable at x equals 0? That's the question. Is it differentiable at 0? Now, do all of you know what the absolute value graph looks like? What does it look like? It's a V. It's a simple V. And we're going to use the graph to help us. Is it differentiable at 0? At the vertex of the V? Okay? I will tell you that the answer is no, and I'm going to prove it to you. Okay? Now we're going to kind of look at this in a graphic perspective, because in reality there is no derivative for absolute value. You would have to, its absolute value is 2 pieces of line connected at the origin. Do you all agree with me?
Yes.
Does anybody happen to know what the equation of this piece of line is right here? That's y equals x, isn't it? What about the other side? What is its equation? So it's really a piecewise function, and that's what we're really going to be looking at today, is piecewise functions, because those are the ones that really have the most non-differentiable points. So that is really 2 pieces. So we cannot take a derivative of this function as it is, because it's really piecewise. Okay? So, first test. Is it continuous at x equals 0? Is an absolute value graph continuous at x equals 0? Is there a hole there? No. So it is continuous. The answer is yes, it is continuous. Now let's look at the limits of the slopes. Now, I told you that we're not going to take the derivative algebraically for this one. We're going to do one similar to it in a little bit. The limit as x approaches 0 from the left of the derivative is what we're going to look at first. Okay. What is the slope of this piece of line? What's the, no, not the equation, what's the slope? It's -1, right? Now the slope is -1 at every single point on that line. Do you agree with me? So as I get closer and closer to 0, it looks like the slope at 0 should also be what? -1. So the limit of the slope of the left-hand piece of line is -1. The limit as x approaches 0 from the right of the derivative means I'm now looking at the slope of the right-hand piece of line. What is the slope of the right-hand piece of line? 1. And it's 1 at every point, agreed? Therefore, if all you had was the right-hand piece of line, it would look like the slope at 0 should also be 1. Are those two slopes the same? No. Those two limits are not the same. So we can say since the limit as x approaches 0 from the left of the derivative does not equal the limit as x approaches 0 from the right of the derivative, f of x, the function, is not differentiable at x equals 0. Let me move that up for you. Yes?
How do we know when to write there?
From here on out, we're going to. For this first example, just to kind of prove the non-differentiability, we're writing the whole long sentence. But for the rest of the examples I'm going to do is going to be a therefore. Okay? So since the limit from the left of the derivative is not the same as limit from the right of the derivative, it's not differentiable at 0. Okay? Now think of it this way too. Differentiable means that you can draw a single unique tangent line at the point in question. Okay? Looking at that point right there, could you draw a tangent line to absolute value at 0? Could you draw 1? Well, is the x-axis tangent to the absolute value? Yeah. Okay. But I could also draw another one slightly at a diagonal, couldn't I? Then it would only touch absolute value at one point. I could draw one diagonally this way. So there are multiple tangent lines I can draw at that point. That is another reason that it's not differentiable, because differentiability means it's got a unique slope at that point. And in this case, it doesn't. Okay? Questions? All right, let's go on to some examples of problems that you're going to see on the worksheet that goes with this. Here is what it's going to look like. Example. I'm very crooked. There we go. Part A is going to say determine if f of x is continuous or discontinuous. Determine if f of x is continuous or discontinuous. That's the first thing you're going to do. And then the second thing you're going to do is determine if f of x is differentiable or not differentiable. So is the function continuous or not? Is it differentiable or not? Okay. So here's our first function. F of x equals x minus 2 for x is greater than or equal to 2, and negative x plus 2 for x is less than 2. We're going to do this one completely algebraically. And we're going to come back to graphically in a little bit. So, part A. Is it continuous or not? Do you remember how we did this? We've done this on a quiz already. The three things we have to check are what again? Left-hand limit and f of x in this case, f of c. What is my c in this case? 2 is. So we're going to do the limit as x approaches 2 from the left of the function itself. And we're going to do the limit as x approaches 2 from the right of the function. And then we're going to do f of 2. So the three things we have to check, we're going to see if they're all the same. And mathematically prove whether or not this is continuous. All right, for those of you who need the number line, I'm going to go ahead and draw it on here. Here's the 2. Which equation is defined to the left of 2? The second one is. Let's number these real quick. So 1 is on the right. Which one is on 2? 1 is. Okay. So 2 from the left would be the second equation. I'm plugging in 2. So it's going to be negative 2 plus 2. So this limit is 0. 2 from the right means I'm going to plug 2 into the other equation. So that's 2 minus 2, which is also 0. So we're looking good as far as continuity goes. So f of 2 is the first equation. I've already done the math, so all I got to do is write the answer down. So is this function continuous at 2?
Yes.
Yes. So we just write our therefore f of x is continuous at x equals 2. And we don't have to explain why. The work itself in this instance does. Okay? Part B. Now let me ask you a question before we do part B. If we had found out that f of x was not continuous at 2, is there even a chance that it could be differentiable? No. So that's kind of the beauty of a situation when it would come out to be discontinuous. So if this came out to be not continuous at 2, all you would write on B is since f of x is not continuous at 2, it's not differentiable at 2. And you don't have to do any math. You just have to write the sentence down. Okay, and then you're done. But this one is continuous, so we need to keep going and see if it's differentiable also. Okay? Now, the way we do that is we have to say, first of all, it's continuous, which we know, and the second of all, that the left and right-hand limit of the what? Derivative have to be the same. So, the first thing we're going to have to do is take the derivative of this function. So I'm going to draw a big arrow going down there. I've got to take the derivative of that function. How do you think I'm going to do that?
Does it matter whether because we can't do it the long way, right? Because you said we won't do that anymore?
Correct. We won't do it the long way anymore. So could I use the shortcuts on both of those functions?
Yes.
Yeah. Each one is a piece of graph, so I take the derivative of each piece as I see it. So we're going to draw the piecewise functions thing here. What is the derivative of the first equation using the shortcut?
1.
It's just 1. And we write x is greater than 2 but not equal to. Very important that it's just greater than. And I'll tell you why in a minute. I don't know if there is a slope at 2. If you put an equals there, you're telling me there is a slope at 2. Okay? Because I don't know yet. Now, what is the slope of what's the derivative of the other equation?
-1.
-1. So -1 for x is less than 2. Now, I'm going to draw a little arrow. I'm going to write myself a note. And I want you to copy this too so you have it for future reference. Do not include equal sign because we do not know yet if f is differentiable at x equals 2. Do not include the equal sign because we do not know yet if f is differentiable at 2. Because if you put it, you're telling me that it is. At the end, if you come out that it is differentiable, then you go back and add it on. But not yet.
So whenever we work these out, we have to draw this like piecewise.
Yeah, you're going to start with a piecewise function, and then you will have to take the piecewise derivative, yes. Okay. Now we need to test the limits on either side for this. So we're going to do the limit as x approaches 2 from the left of the derivative, and the limit as x approaches 2 from the right of the derivative. Okay, the number line is the same for the function as it is for the derivative. So the left-hand limit will be the second equation. What is this? What is the limit of negative 1?
Negative
Is it negative 1 or is it negative 2?
Negative
1.
It is negative 1. There is no place to plug in the 2, so we don't even use it. Does that make sense to everybody?
Yeah.
Okay. What about 2 from the right? That's the other equation. What is its limit?
1.
Positive 1. So is this function differentiable at 2?
No.
No. Okay, so we just write, therefore, f of x is not differentiable at x equals 2, period. So we proved that it was continuous, but it's not differentiable. Does this make sense to y'all?
Yes.
This is what I'm going to be asking you to do. You have to do the continuity step, then you do the differentiability step. And once again, I'll tell you that if this came out to be discontinuous, you just have to write a sentence saying, because it's discontinuous, it's not going to be differentiable. And you don't have to do any work. Questions? I have one more example to show you, and then we are done with notes. Oh wait, I got to show you graphically some stuff. So I'm going to draw a line right here. Let's talk about, first of all, what are the 3 types of discontinuity? Do you remember? Jump, point, and infinite, okay? There are also 3 types of non-differentiability. So when you look at a graph, you can know whether it's not differentiable or if it is. 3 types of non-differentiable points. Okay, we've already looked at one of them, but I'm going to start with a different one, because these kind of fit together in a certain way. You've seen this first one before. It looks like this. When 2 points come together like this, we had an exploration on that. Do you remember what that's called? It is a cusp. Very good. So the first type of non-differentiable point is a cusp. Okay? Now, this is an obvious thing that it's going to be not differentiable. Are the slopes on the left of this point positive or negative? Slopes over here are positive. Slopes over here are they ever going to become the same thing? No, because they're just getting steeper and steeper. They're just getting bigger and bigger on both sides, so there's no way they're going to meet up. Number 2 is what we just did in an absolute value, and that's called a sharp corner. So one is a cusp and another is a sharp corner. And this begs the question, well, what if one side is straight and the other side is curved? Well, you can call it whichever one you want. I usually call it cusp if it's curved at all. Okay, the third one is kind of weird. And what it is a situation where a graph is going along, it all of a sudden goes straight up for a split second and then turns this way. And right there, the tangent line is straight up and down. And that is called a vertical tangent. The graph of the logistics curve, which I think you learned last year in pre-cal, has that, as well as the cube root graph has this as well. It's a vertical tangent, where basically the limit as x approaches a of the derivative is positive infinity, because it's going straight up. The slope is positive. The limit of the slope is positive infinity. That's why it's not differentiable at that point. Yes?
Isn't a derivative a slope?
Yes.
Okay.
Yes.
Where the asymptote is that a point on there?
Okay, this is not an asymptote.
Oh.
It's a tangent line. That's where the tangent line is, and the tangent line is straight up and down. And it actually crosses, there's no way to draw a tangent line there. It goes straight through, it goes through the curve, actually.
But that is a point, right?
That is a point right there, and that is the point where the slope is undefined. It's infinite slope. Okay? Any questions? All right, last example. Last example. Find the values of A and B that make the function differentiable. Find the values of A and B that make the function I'm about to give you differentiable. You guys took a continuity quiz a few weeks ago, and the last question on the bottom of that quiz gave you a function with A's in it, and you had to solve for the A or the C or something to find what value would make it continuous. Do you remember that?
Yeah.
Okay, we're doing something similar to that, but in this case, we're going to have two variables. Okay? So here is our function. F of x equals 3 minus x for x is less than 1, and ax squared plus bx for x is greater than or equal to 1. 3 minus x for x is less than 1, and ax squared plus bx for x is greater than or equal to 1. Okay. It says to find the values of a and b that make the function differentiable. Okay? So we are going to eventually have to take the derivative, but I'm just going to drill this in your head to make sure you get it. In order to be differentiable, it has to first be continuous. So we have to test the continuity first. So step 1, check the continuity is what we're going to do first. And we're going to do it pretty similar to the last problem, except we're going to have some unknowns in here. We're going to check the continuity. So we need to do the limit as x approaches what number? What's 1, because 1 is the only point in question. 1 from the left of the function, and then the limit as x approaches 1 from the right of the function, and then f of 1. So we're going to do those three. Left-hand limit, right-hand limit, f of 1. So now, let's do our little number line for those who need it. Equation 1, equation 2. Which equation is to the left this time?
1.
1 is, and then 2 is on the right. And which one is at 1? 2 is. Okay? So the left-hand limit would be the first equation. So if I plug 1 into the first equation, I get 3 minus 1, which is 2. Okay, that was easy. Be careful with the right-hand limit. What am I plugging 1 in for again? X. So what would this one look like after all is said and done? What would it clean up to be? A plus B. That's it. Correct. Now what is f of 1? Which one is the f of 1? The 2 or the a plus b? Oh, a plus b is. Okay. We are purposely trying to make this function differentiable, which means we have to make it continuous. Okay? So these three have to be equal to each other. 2 of them already are. So how can I write a math sentence to show that the last two are? What would it say?
A plus B equals 2.
A plus B equals 2. So A plus B has got to equal 2. Agreed. I agree with that statement. Okay. Can you tell me, beyond a shadow of a doubt, what two numbers A and B are?
2 and 0.
It could be 2 and 0. It could be 1 and 1. It could be 10 and negative 9, right? It could be fractions. So I don't know yet what A and B are. I don't have enough information. Okay? So there is a mathematical rule, I can't think of it off the top of my head, that says if you have two unknowns, you have to have two equations to solve for them. I only have one equation right now. A plus B equals 2. That's nice, but that's not enough. So now we got to go another step. Step 2 is to check the differentiability. Okay. Check the differentiability. Now, in order to do that, what do I need to do to my function? What do I need to do to my function?
Find the derivative.
I need to find the derivative. I need to know what the derivative is. So, here we go. Move it down. F prime of x equals. It's another piecewise function. First equation should be no problem. What's the derivative of the first equation? Careful. Negative 1. Comma, x is less than 1. Now, carefully look at number 2. Think about what its derivative would be. Don't say it just yet. Just think about it. Okay, turn to somebody sitting next to you and say what you think the derivative would be.
2ax plus
2a plus b.
A lot of you sounded very similar.
2a.
Okay, the 2 comes down and multiplies to the a, right? And then x's power drops to 1 plus the derivative of this, that's a 1 on the x, so that's bx to the 0, right? Just b. Y'all did great. Greater than 1. Okay. Greater than 1. Not greater than or equal to, just greater than. Okay. So we're going to now do, I'll do it over here, the limit as x approaches 1 from the left of the derivative, and then limit as x approaches 1 from the right of the derivative. I don't need the equation anymore, I just need the derivative. So I'm going to get it out of sight. If you need to look back up at the number line, you can. Which equation do I plug in for the left-hand limit? First or second? First. So what is the limit? -1. That was easy. Okay. What is the right-hand limit going to be?
2a
2a plus b.
2a plus b.
Just 2a plus b, because x is 1, remember? 2a plus b. So, in order to be differentiable, those two things have to be equal. So my new equation is what? 2a plus b equals -1. And there's equation number 2. So I'm going to kind of, I did this in a little strange order, so I'm going to draw a little arrow over there. The two limits equal that. So we have a plus b equals 2. We have 2a plus b equals -1. Now that we have two equations, we can solve for a and b. Does anybody know how?
Divide 2a.
Substitution or elimination.
Tell me what you were saying.
divide 2a. So divide 2 from the front, like the coefficient from that
No,
side.
no, 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 no. Set the first equation equal to a, and then plug it in the second.
Okay, is that what you were gonna say? Take the first equation, set it equal to A, plug it in the second one. That is a very valid way to do it, and it's called substitution. But I want to show you another way that's a little bit faster. Would you like to know a little bit faster way to do it?
Yes.
Teach me, of course. So, step 3 is called solve the system. What you have here, when you have two equations with two variables, it's called a system of equations. So we have a plus b equals 2, 2a plus b equals -1. And we draw a line like we're going to add them together. And as though if I add them together, I'm going to get 3a plus 2b equals 1, which doesn't really help. Just creates another equation. But if I take the second line and I multiply everything by -1 first, the b's are going to cross out, and then I can solve for a. And that's what I'm going to do. So we multiply everything here by a negative, so the a and b turn negative, and the 1 turns positive. And now we add the two lines together, and we get -1a equals 3. So a equals -3. See how quick that was? Now, how do I find b? How do I find b? Plug in a. Does it matter which equation I plug it into? Do you think?
Well, no.
No, it doesn't, because what we're finding is the coordinates of a and b that they have in common. So it doesn't matter which one you plug it into. So I'm going to come up here and put in -3 plus b equals 2. So what does b equal? 5. Got to get the brains going again after lunch here. Okay, now, have I solved the problem that I was trying to solve?
Yes.
Have I answered the question that the problem asked? Go to the beginning of the question, look.
Yes.
It said find the values of a and b that make the function differentiable. Did we find the values of a and b? Yes. Are we sure they work? Well, let's check and see. You do not have to check on the AP exam, but we're going to check this one just because it's the very first one we've done this way. So we're going to check. And I'm going to show you the really fast way to check. So we're going to take the original function. We're going to put those a and b values in. 3 minus x. X is less than 1. -3x squared plus 5x. X is greater than or equal to 1. Move it up. Now, in order to be continuous, when I plug 1 into both equations, they should come out to be the same answer. If I plug 1 into the first equation, what do I get? 2. If I plug 1 into the second equation, what do I get?
2.
I get 2 again. So that means it's continuous. That's the very unmathematical way to do it. We're doing math, but we're not writing anything down. We're just doing it in our heads. Both equal to when x is plugged in. Okay, now I'm going to kind of come down here because I'm running out of room, and I'm going to take the derivative of each of those as they look. This is good derivative practice anyway. What is the derivative of the first equation? Careful. -1. And the second equation?
2ax.
Careful.
5, -5.
-6x plus 5. X is greater than 1. And I'm going to put the equals on if it's right. If I plug 1 into both of those equations, do I get the same answer? If I plug 1 in here, well, it's just going to be -1. If I plug 1 in the second one, I'm going to get -1. So both equal -1 when x is plugged in. And so check, it works.
Do we have to write that part?
No.
Ran out of space on it.
No, you do not have to write that part. This is a one-time check. We didn't have to do it, but I'm doing it just to show you that it worked.
So A and B is not like, A and B is numbers that we came up with to make it a differentiable equation.
Yes, A and B are numbers that we came up with to make the function differentiable. Exactly.
Like, we could have put in any number and then, I mean, it might not be differentiable, but it would still.
It would still make an equation.
Yeah.
Yeah, it would still make a piecewise function, but it wouldn't be a differentiable piecewise function. Yes. And A and B could be anything, but the only ones they could be to make it differentiable are what we found. All right. Any questions?
And so when you check, you should check using both f of x and f prime.
Yes, because it has to be both continuous and differentiable. It has to work in both.